welcome. Cool, everybody can hear me. My name is Scott Carter. I lead product management for Cisco 8000 Fixed Systems. Let's go ahead and burn this one down. As with all the breakout sessions, go ahead and follow along with the app. You're gonna have access to the WebEx team space. You can ask questions. We have some moderators in the room that are gonna help direct those questions to the right place or answer them directly. Excited to talk about building Ethernet AI fabrics on Cisco Silicon One. I'm going to start kind of with a brief overview of where the industry stands today, then hand it off to my counterpart to talk about all the challenges that you're going to see trying to build out an Ethernet AI network. I'm going to bring it back and show you how to build that on Cisco Silicon One and Cisco 8000 devices. We'll then go ahead and wrap up with kind of a discussion of Ultra Ethernet, one of the trends that's on top of minds these days. And then we'll wrap it up with if there's any questions in the room. I'll give you a moment to kind of absorb this quote. I know it's an internal one, but it should tell you something about the direction that the market's going. And while we're at it, let's go ahead and ask a couple questions of ourselves about, is InfiniBand the right network type to kind of carry us forward into the next wave of AI? What network type allows me to scale most effectively? What network is going to be most performant at scale? What happens when I start adding a lot of simultaneous jobs in a multi-tenant environment? Can I keep my customers' data private, sovereign, and protected? You also have operational considerations. Is there support for visibility, debuggability? Am I going to be able to hire experts who understand this technology easily? And then am I going to be supported by a number of vendors in the ecosystem? Now, the answer to most of these is, of course, with enough time and money, maybe. But with Ethernet, the answer is absolutely, on all counts. It's not just me saying it. You'd expect the product guy, of course, to be raving about how great AI or how great Ethernet is for AI, because I make a living off of selling Ethernet hardware and software. But the market research analysts are saying the same thing. All right, they're saying today that the market is already at 44% Ethernet, and in 3 years, that's going to be 74%. I should note that this number is just for switches. It doesn't include optics or NICs. By and large part, a big part of that growth is because of the explosion in inference investment. It's going to triple over the same time period, from 15% to 46%. Who's driving this growth? It's all the hyperscalers. And then the rest of cloud that wants to be like the hyperscalers. The Synergy Group, another market analyst, says that 90% of the power provisioned for the data centers that are in planning and those power contracts are already gobbled up by the hyperscalers. 84% of the total data centers by count. So where does that leave the rest of cloud? Where does that leave enterprise? And then I know we have some SP friends in the audience. We're going to have to do better than that 2%. Especially because you're sitting on some of the best real estate for addressing the needs of inference today. Let's take a look at the overall landscape for AI. And this is very oversimplified. It's not true in all aspects, but it helps to kind of frame our thinking about what kind of network we want to build, what workload is going to be run on it, and what kind of hardware and software I might need. So on one end of the spectrum, in this dimension, you have inference. You might be an enterprise customer trying to deploy a self-built model. You have a relatively small cluster size, and your traditional ECMP is probably going to work because you're not scaling up to the thousands and thousands of GPU clusters that are being trained by some customers. On one side, you could have a disaggregated NOS, although this isn't true in all places, but you could have a vendor NOS. There's different ways of addressing the congestion that these networks face, and my counterpart is going to go through, the intricacies of traditional Ethernet, enhanced Ethernet, scheduled Ethernet. But across all these dimensions sits Silicon One. Silicon One addresses all points across the AI spectrum. Attention is all you need. We've all heard that, right? That's a basis for AI training models. Well, that is untrue. You need crap tons of capital, dollars, and you need tons of energy in order to run these. So this chart is the AI accelerators that are available on the market today, or are in planning or announced. Below the line is the scale-up domain. This is how many accelerators that you can fit inside of a high bandwidth, let's call it a chassis, although we're seeing this kind of expand outside of the chassis as well. The scale-out domain is what we kind of consider a traditional networking area, where you're interconnecting with a bunch of switches. Now, the first thing you'll notice is that one side of the equation has 18 times the bandwidth of the other. NVIDIA, AMD, they've kind of built to this ratio. And it's a fixed ratio because it's built in the silicon itself. Now, I don't want to discount how good NVLink and Infinity Fabric are at doing the kind of workload they have here. It's much harder than networking. You're having to do memory semantics, memory verbs. You're having to deal at a hardware level, something that is more analogous to PCIe or CXL. But it's still a network that exists inside the box. Now, Intel, they've done something pretty novel in this area. They said, let's build the Ethernet controller directly onto the accelerator itself. This gives them a lot of flexibility, because the workload today, text-based LLMs, is not going to be the same as a workload tomorrow, which could be multimodal or something completely different. I've put a hypothetical custom GPU up here just to kind of illustrate that point. Ethernet brings flexibility to both scale-out and scale-up domains. The need for compute is growing faster than Moore's law is indicating. It's doubling more or less every 6 months. The green dots on the chart behind me show the amount of flops needed. And this is a logarithmic scale, so the slope of that line is exponentially steeper. Fortunately, we have things like parallelism scaling out to thousands and thousands of GPUs in a supercomputing style network that help to address the need for more and more compute. The blue dots are the amount of days of time spent in training for kind of the household name models. You'll notice that they are not all uniform. Right, they don't exist on the same kind of spectrum. This is because the variety of accelerators in the market, as well as the scale at which they're deployed, has a huge impact on the training time that it takes. And you can bet that everybody who's doing training in their data centers right now is trying to minimize that training time. In fact, just last year, open source Llama with 65 billion parameters was revealed by Meta to have taken 21 days to train. Today, with a 32,000 GPU cluster, that same model can be trained in 1 day. With all these GPUs trying to communicate with each other, utilizing links at 100%, causing a ton of congestion. Congestion can be causing delays in your network. Your network is getting in the way of compute, causing GPUs to be idle, missing out on available compute and energy. It's a waste of capital. So what do we do? How do we optimize that GPU investment? How do we get the network out of the way? Now, I'm not going to claim to know how to, but I know somebody who does, and it's my great privilege to introduce Ramesh Sivakalundu. He's our Director of Technical Marketing and Architectures, a longtime Cisco veteran, worked on every switching platform going back 25 years, with very few exceptions. Go ahead and take it away, Ramesh.
Thank you, Scott. So moving on to what is an AI workflow and why do we need so many GPUs and why do the GPUs need to communicate with each other? Let's look at the two different AI applications that are possible today. One is recommendation models, and the other one is large language models. Each of them brings a separate characteristics required from a cluster for training and also for the application to provide the end result. DLRM, which is the deep learning recommendation models, they're basically used for search, feed ranking when you are in your social media, ads and the related contents that need to be provided for the ads that are showing up in your feeds, and recommendations if you search for something that you are looking for. The inference engine, which drives these DLRM models, need a few gigaflops for producing what the industry calls as time to first token, which is the time measure to see how well the inference response comes to the user. That's directly related to the user experience. You want to minimize your time to first token, and you could keep feeding more data for your inference engine in the background while the user is consuming the first response. It's a narrower scope typically. It's industry vertical specific, and you're focused on that specific sector. And training takes about 100 gigaflops per sentence that is there in the recommendation model. In contrast, the large language models are designed for processing natural language or in a human language. Training that takes approximately a petaflop per sentence that is being processed by the model. And it generates intelligent responses, creative responses that could be called what the industry calls as generative AI. And the inference needs are like tens of petaflops for a 1 second time to first token. So it's a little different when you are dealing with LLMs versus recommendation models. An improved user experience, it means a faster time to first token, and that requires a distributed inference handling of the various trained models, and that distributed networking is an imperative in this case. So let's look at the AI/ML workload itself. What happens in a typical AI/ML workload? There are a bunch of GPUs. They execute commands, and they are highly capable of saturating a 400 gig link today. And they can use that links to communicate with each other, and they're clustered together in a single enclosure or a system node, and then they are networked using the scale-out network that Scott was talking about, using either InfiniBand or Ethernet switches. Once the GPUs have finished their execution of the command, they need to send the results, or it could be the final results or the intermediate results, to each other in the cluster. Different collective operations or communication methods are used for sending these intermediate results. We'll talk about one specific collective operation which puts the highest bandwidth requirements and processing requirements, which is called all reduce. In all reduce, every GPU's results are merged together and sent back to everybody else to continue the iteration in the model itself. Could be a next level of, or could be multiple data sets broken down, being processed, and then combined together. So that results in communication that happens over the network. And then once everybody is finished processing, there is an event which is called a barrier or a synchronize, which basically means GPUs can't continue processing till the results of every other GPU has been reduced, collated, and sent back to every GPU. And this happens periodically during the training process. And during this time, the last message from the last GPU is holding up every other GPU in the network, in the cluster, and that's a wasted GPU compute power. The industry calls this measure as the job completion time, And the last GPU that's delaying the whole job completion time to be move on to the next process in the job is the tail latency. And the goal of everything that people are trying to do now is to reduce the tail latency. So if you look at a typical data center, and it's running any of the traditional applications that run today, the network traffic is chaotic. Yeah, go ahead. It's not just, we don't want to drop packets A, but we also want to make use of the entire bandwidth in the network. The cross-sectional bandwidth, I'll get into that. So if you go into traditional Ethernet versus what we, the enhanced Ethernet versus scheduled fabric, we'll talk about the differences and how all the issues that I'm pointing out now gets addressed in one of the three different kinds of Ethernet. So if you look at a typical data center, the traffic pattern is chaotic, it's random, there's no, you can't find a pattern in the data throughput that is being utilized by the network, and many small asynchronous flows are basically being used between multiple clients and servers to talk to each other. If you look at an AI application running on a GPU cluster, and doing this communication between GPUs periodically, there's a burst of communication almost synchronous, mainly because everybody starts processing the data that they have been assigned to process at the same time, wait for the results to be computed, reduced, and shared back again, and then they restart. So it's a cyclical, repetitive burst of traffic on the network, and there is a period of time when everybody is done communicating, but they are waiting for the results to come back, and one GPU being slow causes every other GPU to be waiting for the data. And that's the situation where GPU is stalled, and you're not getting your bang for the buck for the GPU that's basically waiting for the results. So I'm going to list tips. This slide is there for your consumption down there later if you want to look at the various collective operations. The circle with number represent a GPU or a rank in your cluster. The colored boxes, like square boxes, are messages. And the squared boxes with numbers represent messages coming in a specific sequence order. And all of these messages from the various GPUs go through a function which could be reduce, could be just reduce and scatter, could be scatter, could be broadcast. So that's the different kinds of collective communication processes that exist to communicate with each other. Barrier is basically stopping everybody to synchronize, and barrier could be without data or with data. All reduce is barrier with data. A barrier without data, it will be just a barrier call to the communication protocol. So how do you minimize your tail latency and minimize your job completion time? That's the mantra everybody is chasing after with all the innovation that's happening in the networking space, in the compute space, and how do you do that? There are three things that contribute to the tail latency and job completion time. Congestion in the network, how well you load balance across all available links, and link failures. A failed link causes the packets to be buffered and dropped, and that's not helping the job completion time. Congestion in the network, if you don't react to the congestion, you're going to continue to increase the buffer utilization, and you're going to eventually drop packets. And load balancing, you have multiple paths from any source to any destination. If you don't use all paths that's available to you, today we use traditional networks use ECMP hash of a flow. You could get flow polarization, and you're not getting an equal distribution of all your flows across all multiple paths. You're going to create congestion. So those are the three main bullets that you need to remember. It's contributing to job completion time, and how do you address those three things is what we're going to talk about today. So there are three options. Ethernet, enhanced Ethernet, or scheduled Ethernet. And each of them address a specific things that helps improve the overall performance of the network. Improve the overall performance of the network. And let's talk about load balancing. For traditional Ethernet, it's a stateless, equal cost multipathing. You take the phi tuple of the packet, you hash it, you pick a path, and if you're lucky, you get a better distribution. If you're unlucky, you're going to just saturate one link. Enhanced Ethernet is an enhancement to ECMP, but there's some state that's maintained in the network. And when the flow is idle, you could basically decide, okay, I'm going to now switch my link utilization on that particular path that was selected before is more than what I want it to be, so I can now switch the flow to a different path which is less utilized. But it has to happen when the flow is idle, and so you need to maintain some state to remember to figure out when the flow is idle. Enhanced Ethernet also has this concept where now you could just spray the packet across all available links, and the receiver NIC can reorder the packets. If you don't care for the order of the packets, use all your links in your network and spray the packet across. But it requires reordering on the NIC. Scheduled Ethernet allows you to spray, and the leaf TAR connecting to the receiver is going to do your reordering. And that's one way of, when you spray a packet, you are basically cross-sectional bandwidth utilization of your network is automatically going to increase. So those are the three options that exist. With Silicon One, you could build your platform today and pick which one you want to do and switch from one to other. It's totally software programmable for you to change that. Let's look at load balancing. That was one of the bullet points which causes JCT we looked at in the previous slide. Congestion management. Today's traditional network uses early congestion notification. It's basically packet experience congestion. You mark it in the packet. The receiver then reflects it back to the sender so that you know there was a congestion. That's a round-trip delay to get the notification back. You could get advanced telemetry from the network and infer congestion and try to change the path if you can do that in a situation where the packet can be reordered. That's the enhanced Ethernet way of handling congestion. In a scheduled Ethernet, you have a mechanism which has a VOQ at each for the virtual output queue for each of the destination. And then there is a mechanism to do a request grant before the packet is sent to the destination. You are avoiding congestion when there's a request grant mechanism. So that's the way scheduled Ethernet is addressing congestion. You could pick one of the three solution, whichever makes sense for your application. We'll talk about where each of these makes sense from your size of your network and the kind of applications you're running in the slides below. Link failure. Today, BGP has to get involved and change the route for you to handle link failure. In enhanced Ethernet and scheduled Ethernet, we have mechanisms in the hardware to detect a link failure and avoid that path when you're spraying a packet across available paths. So that's how you handle link failure. A hardware mechanism is much faster. It's going to react in microseconds relative to what software has to get involved. So your job completion time reduces because it's hardware detected link failure. So if we look at the job completion time, if it is good in Ethernet, we are saying it's better in enhanced Ethernet and it's best in the scheduled fabric or scheduled Ethernet. There is a coupling between the NIC and the AI fabric. In the case of Ethernet and enhanced Ethernet, where you're just doing stateful flowlet-based load balancing, there is no coupling between the NIC and the fabric. In the case of spray and reorder in the NIC, there is a coupling because now you are relying on the NIC to do the reordering, and there is no coupling in the case of a scheduled Ethernet. And any of these three options could be used as a front-end network or a back-end network. Scott's going to go over what a front-end network is and what a back-end network is in the next few slides. It could be used for training and inference. So let's look at what is parallelism and why the GPU clusters are being put together with 32K GPUs. How do they use those GPUs? They have to break down the problem space into multiple smaller sections and then assign those smaller problems to a set of GPUs. And that's what parallelism brings. And there are multiple types of parallelism. I'll walk through all three of the parallelisms and then identify which parallelism makes sense for which application. So data parallelism. Here, this is very specifically used when the data set is too big. A single GPU can't handle all the entire data in its memory space. So you break down the data set into multiple smaller sections. And the same data, same model is utilized for each of the data set. And then the processing happens on the GPUs. And then in the end, the results are collated together. It's effective when you're dealing with vast data sets. And the main goal here is to basically say how much a GPU can hold in its memory, and you basically break down your data set based on that. Model parallelism. Here, the model is too big to fit in one GPU, so you're going to break down your model. You could be multiple iterative layers in your model. You break down the model into smaller sections, and the same data then is applied to each of the subsets of the model, and then the results are again combined together. It's beneficial when you're dealing with extra large models, and each segment of the chunk of that in the parallelism is processed on one single node. Pipeline parallelism is you are basically when your workflow is organized in stages, you break down your pipeline of your workflow. A subsection of your pipeline then runs on each GPU. It's useful in scenarios when there are sequential steps in your training model. You basically break it down, and then you apply it to the cluster. Where do you use what? When your memory efficiency is your goal, and your data set is not that big, but you still can live with without data parallelism, you apply model parallelism and pipeline parallelism. And that's how typically the inference applications are running today. They basically don't have, the model has been trained with the data set. Now we are using the model to do your inference application. You can break down your model now into model parallelism and pipeline parallelism, and your data is basically the inference of whatever the sentence or whatever your application is processing to produce the inference. 3D parallelism is compute efficiency is the target. You basically want to use every GPU possible in your cluster. So you break it down into data parallelism first, then you do the model parallelism and pipeline parallelism to do your training. So training applications typically tend to use 3D parallelism. Inference tend to use 2D parallelism. You could do either or on any kind of parallelism, but the choice is based on your application and the model and what you're trying to train based on your data set, the number of parameters in your data set, how big your data set is. So it's a complicated decision making to decide which kind of parallelism and how you want to build your cluster. There's one more parallelism that exists in the industry today, which is called expert parallelism. If you have a model that is tuned for one set of application, and another model for the same application that can, based on a different set of parameters and data set, now you want to basically take the results from both your models and then pick the best result possible as your inference result. This is basically saying now you have multiple trained models. I'm going to run my inference on all the trained models and then pick the best possible result. That's a model of experts, or MOE parallelism. Here now we are distributing each expert model onto the GPU cluster, and each GPU then is working on a single expert model. So we've looked at every kind of possible parallelism that exists today. But why do we need this parallelism? It's mainly for efficient management of the cluster. You make it scalable, flexible, and how do you now optimize the cluster computation collaboration which happens periodically as the model is being trained, and the efficient data transfer between those GPUs. And what can Cisco do there? Get the network out of the way. We can efficiently utilize the cross-sectional bandwidth with either enhanced Ethernet or scheduled Ethernet, build this into a class-leading silicon, hardware, software, and the product offerings that Cisco have based on those silicons. Be open, be extensible, be adaptable. So we run SONiC on top of our Silicon One platforms. Ultra Ethernet, we'll talk more about it. It's an open standard for how AI clusters can communicate better than what they're doing today. And Ansible, playbooks for and Grafana. All these are tools that we provide that can run on Cisco's platform today. That said, I'm going to hand back to Scott. He's going to walk through what are the AI infrastructure options. Thank you.
Thank you, Ramesh. We're actually moving pretty briskly through this, which I think is very uncharacteristic. You can ask my bosses. So I actually think I want to kind of address the gentleman's question about building a better mousetrap. We're not advocating one or the other for all types of networks, right? Ramesh was saying, you know, the metric that we use for training, job completion time, that governs everything. The metric that we use for inference, time to first token, don't necessarily have the same network type. Right? Training is heavily GPU reliant. I'd say that inference doesn't even have to be run on a GPU. It could be run on a single CPU. I mean, we know of our largest customers that are heavily involved in AI training choose to do this in their production networks today. All right, don't buy into the myth that, you know, I need this preset solution, this packaged pod that does everything and costs an arm and a leg to deploy. Think about the workload that you're going to put on it and the type of network. Enhanced Ethernet, scheduled Ethernet, that's really good for training, but you can probably get by with a traditional Ethernet option for inference. In fact, I would argue that latency is a lot more important on the inference side of the network. All right, so what is the best front end for that? Well, it's the front end you have in place, right? Try to integrate AI into that existing front end. Let's talk about the different types of networks. Actually, we just kind of started discussing about what is a front-end network, right? It's a traditional data center that we're all kind of familiar with. Its goal really is to interconnect CPUs, x86, ARM, or storage devices, to connect those between each other and connect those to the outside world, connect those to other data centers. In the case of an AI network, and a GPU system, you have the scale-up network inside the box. Now, this won't always stay in the box because there's massive amounts of interconnecting data inside these GPUs. I mentioned at the beginning that it was an 18-to-1 ratio between the scale-up and the scale-out. The scale-out network's job is primarily to interconnect the GPUs. Right? It's a relatively simple network, but it has to do all the things when it comes to congestion and packet spraying in order to keep that network as efficient as possible. Otherwise, you're wasting, you know, all the time of your collective GPUs and your fabric. So what options do we have? I'm betting everybody in this room knows what a Clos Fabric is. I'm not sure there's anything I could say about a Clos Fabric that you don't already know. Scales incredibly well. Is redundant, reliable, very well understood. As long as you're able to solve the problems that a traditional ECMP network creates. This is a kind of a de facto standard out there for addressing AI workloads. Some of the more exotic ones evolved out of HPC workloads. I love this name, Dragonfly. I mean, that's a great marketing name. I'm surprised it's not more popular. What it does is actually very similar to the Rails approach, which I'm going to show you in a couple of slides, but it exploits the locality within the domains. All right, there's a high bandwidth domain that has a high amount of bandwidth between it, and then the hosts are kind of indexed and interconnected in a cross pattern. This requires a lot of the job scheduling, right? The RICL, the NICL, the TICL, the HICL. Actually asked ChatGPT to write me a limerick about that, and it did a pretty good job. And if you ask me nicely at the end, I'll share it with you. It requires that collective library to be aware of the topology. So it's very dependent on the NICLs or the CCLs. 3D toroidal mesh. Glad I was actually able to say that. It's a very interesting architecture. It means that every host has a north and a south and an east and a west and maybe an up and a down partner. All right, so creating this effective sea of compute where they're talking to their neighbor. Well, the sea of the compute has to have a shore, and that shore is the front end, and sometimes that can be several degrees removed from the compute that's in the center of the sea. It too is very job scheduling dependent, right? That topology has to be known, has to be aware. You have to have a visibility that goes deep in that network. Yeah, totally. All right, one of the things that's not talked about very much, sorry, for those in the back, the question is, is one of the reasons of doing this to reduce cabling costs and optics, yeah. One of the things that's not talked about a lot with AI networks is the failure rate of optics that can kill your job completion time, or even the miscabling of all the cables that have to go between the hosts. You might have a miscabled GPU and it's just acting inefficiently unless you have really good visibility in it. You don't see it, and that's an idle asset. That's just burning power. There's customers that are figuring out all manner of ways, how to kind of take that, take the optics and cabling out of the equation. I think our approach would be, hey, by Cisco optics and cabling, they're built to a higher spec and standard, to a higher reliability in MTBF. The Rails approach, I think, has been most popular of late. It's picking up a lot of steam. I'm going to admit that I originally thought that this was kind of silly. Why would you tie your network architecture to your server architecture? You're locked into something that's not flexible because you're always going to have to buy a GPU server that has 8 GPUs in it, and a certain amount of bandwidth that scales up. Why would you do it? Are you trying to save money? Right? The original white paper that governs this approach was how to build low-cost networks for LLMs. I think a better title for it would be how to scale out beyond the constraints of whatever radix you're working with. The cool thing about the Rails approach is that you can have separate, discrete class fabrics that aren't interconnected anywhere except through the GPUs and that high bandwidth domain. You're already paying for that high bandwidth domain when you're buying a GPU, so why not make use of it? All right? If you take kind of the most common switch that's on the market today, a 32 by 400, and you interconnect it in the class fabric, you can put 64 in the spine, you can put 128 in the leaf. You get about 2,048, actually, you get exactly 2,048 400 gig endpoints, right? That's how many GPUs you can address with a scale out if they're 400 gig class GPUs. Well, on a Rails approach, you multiply that by 8. You're now at 16,000. All right, and of course, the connected libraries that govern this, they know how to send traffic to inside and outside the domain. Quick point on just terminology, because I think it's important. Rail optimized means you integrate a spine into the cloth fabrics that sit on top. So let's see, this right here is showing a rail optimized design. A rail only design, you only have one layer, a single switch, high radix is interconnecting, all GPUs indexed 1 or all GPUs indexed 2. This is actually a kind of nice approach, and I'll show you in a little bit, for what you can do with a very high radix modular chassis, which really in itself a 2-layer cloth fabric. All right, we're gonna talk about product. This is my thing. Actually, no, this chip is Rakesh's thing. We're in our 4th generation of Silicon One. It's our first 5-nanometer ASIC. It's the 2nd generation of our own 100 gig SerDes. It's built into our 8100 series platforms. Those are dedicated DC switching devices. They all run open source community SONiC that's been Cisco validated. They all have kind of the same shared packet buffer magic that has existed in Silicon One since the beginning. In the case of G200, that buffer is 256 megs. These are not deep buffered routing devices. These are DC switching devices. In the case of G200, it's fully output queued. G200 is 51.2 tera. That's 512 100 gig SerDes. The really key to the chip itself is that all of those 100 gig SerDes can be used to address the network. Right? You're not limited in terms of radix. There's a 512 radix. This is the lowest latency device that we've made by far. It's 2x less latency than we had in our previous generation, the G100. Makes use of our 2nd generation 100 gig SerDes, which is helpful for powering cabling, LPO optics. The really strong point for how this addresses the enhanced Ethernet part of the market is things that are built into the hardware itself. All right, topologically aware, congestion aware, and load balancing schemas. Link failure avoidance that happens at hardware speed, it doesn't happen at the speed of a protocol. These are built into the ASIC itself and can be deployed in AI networks to help eliminate the challenges with congestion, headline blocking. It also has some really cool tools for looking deep inside the box. But before we get to that, I want to look at why a 512 wide radix is really important. If you're trying to build a 2-tier cluster, which I recommend with AI network just to kind of limit the latency and number of hops and the complexity, a 512 wide radix allows you to use all 100 gig interconnects and to scale to 32,000 GPUs. All right, that's 512 leafs, that's 256 spines, so 768 total switches. This can't be done in an NPU that can only address 256 endpoints. There you'd have to use 200 gig interconnects everywhere in a 2-tier fabric, and you'd only get half as many GPUs addressed. This is what it would look like to do the same thing with a 256 wide radix device. You'd have to add another tier. You'd have to add again as much you'd have to add 66% more switches into the fabric in order to achieve the same results. All right, so that's 1,280 switches, 66% more, all the included cabling and optics that you need to wire it up. And in a data center that you're trying to get 32,000 GPUs in, you've just spent 1 megawatt more of energy making that possible. All right, so we're talking about how to get the network out of the, oh, sorry, was there a question? We're talking about how to get the network out of the way. But when it comes to building systems, my role in building 8100 systems is to try and get the box out of the way, right? Let the silicon itself be the star. This is what we built first around G200, and I'd encourage everybody to go take a look at it. It is down in the product zone on the World of Solutions. That's right next to the AI Hub, where the G200 itself is on display. There's a bunch of people there who have been trained to talk about it, but you can go see this in the flesh. What we built around it is a 2RU, 64 by 800 gig QSFP-DD switch. It gets all the goodness out of the G200, including the strength of the SerDes. If you were at ORFC this year, you might have seen a demo on this where we had two of these systems sitting on a table. One had fully retimed optics. One had the linear drive optics that are all the rage right now. 700 watt savings between the two by being able to deploy it. And no limitations on where you had to put the linear drive optics on the front faceplate. Speaking of that front faceplate, you'll notice that there's two ports here. Usually, management ports aren't terribly interesting. These ones happen to be connected directly to the MPU. All right, they're high speed. Go ahead. In theory, you can. Right now, we just have back to front in that. But I really want to hear the use case about that, because there's problematic things when you're preheating the air that you're sending across the optics. Yeah, cool side and hot side and all that. So yeah, come talk to me after. I'd love to actually understand that more. These two ports right here, they're called punt inject engines. They're two 25 gig ports connected directly to the MPU, and they can be used to extract massive amounts of telemetry data off of the MPU. Think every packet header, strip out the payload, send it to these ports. And you probably would need a really advanced high-powered collector to ingest that and analyze it. But I can envision a future where you have AI tools that are looking at your packet flows that are traversing these systems and making decisions off of them. So I want to talk a moment about scheduled Ethernet. If you haven't registered for it already, go check out the breakout session 3406 on Wednesday, where they're actually going to do a deep dive on here. We've actually been building scheduled fabrics for years, both with Silicon One and even with other products. We just didn't call it that, but they were really two-tier fabrics that were constrained within the four metal walls of our modular chassis. They did perfect load balancing. That load balancing is incredibly good for AI. And our goal with scheduled Ethernet is to bring that network and unbind it from the constraints of that modular chassis. And that's what we've done exactly here. I mean, this is running on a working image of SONiC we have today. I love these two charts because they demonstrate exactly what Ramesh was talking about, where you have the tail latency that's incurred when every link is, can't be 100% utilized. And so you have the GPUs that finish right here, sitting idle. And when you flip on a scheduled fabric, where you're doing the credit request and grant mechanism, same one that we use inside of our modular chassis, you're able to perfectly synchronize and orchestrate those traffic patterns, have a deterministic job completion time that's 2 times better than what's on the left. Standard ECMP and Ethernet. Again, if you have the time on Wednesday, go check out this breakout session if you want to know more and how we're envisioning bringing this to market. Okay, last point I'm going to talk about is how you can actually address AI with modular systems. There might be a number of reasons you want to do this, but I think the number one reason here is simplicity. All right, each one of my 8818 chassis running the latest line card, which is 36 by 800, or you can think of it as 72 by 400, can address 1,296 ports of 400 gig. If I make each chassis a rail, I get to multiply that number by the same number of GPUs that's inside the box. So instantly, I'm able to scale to 10,000 GPUs. With only 88818s, glad I got through that. Less optics, less cabling, because the actual fabric inside the system itself is just electrical interconnects. You can't accidentally miscable it. Less complexity, and of course the complete redundancy, because we built these things to be carrier grade. We overbuilt them in a lot of cases. All right, so I am gonna stop right there. Are there any questions before we go into Ultra Ethernet and trends? All right, take us home.
Okay. So, talk about what's the industry trending towards. Before we do that, let's look at what's used today when somebody builds an AI cluster with RoCE v2 as their protocol of choice. They have to deal with priority flow control. Every time you do a priority flow control, you need buffering to be able to absorb whatever is in flight. So it requires additional buffering in the network. PFC causes victim flows. So when you other flows of the same priority are also impacted by a PFC. Once you have congestion in the network and you have triggered a PFC, the congestion grows as a tree towards the towards the downlink of the network itself, and it causes more PFC storms. So PFC is a dreaded thing that everybody in the industry has to live with today when they are using RoCE v2. Every time you drop a packet in the network, the transport protocols at the end hosts have to retransmit the packet. And when you drop one packet and this subsequent packet still makes it to the network node point, to maintain order, you have to retransmit go back end. So you basically have to keep dropping packets and wait for the first dropped packet to show up again. So that's a go back end retransmission. Congestion control is totally reliant upon pause frames, and retransmission timeouts. So that's how today RoCE v2 works. The goal of Ultra Ethernet was to address all the pitfalls of RoCE v2 using the Ethernet as the network of choice to get the benefit of Ethernet, cost effectiveness of Ethernet, but be as performant as a supercomputer interconnected with InfiniBand or any other technology that supercomputers are built today. And be scalable to be used as a cloud data center. That was the vision of Ultra Ethernet when the consortium was formed about 1.5 years ago. They called it a new era needs a new network, and it's called the Ultra Ethernet. The companies listed in the bottom are the founding members of the Ultra Ethernet Consortium. Started out with AMD, Arista, or Broadcom, Cisco, Eviden. So there you see a pattern where there is silicon vendors, system vendors, software vendors, companies that build AI fabrics and use it, like Meta, Microsoft, Oracle Cloud. So those are the distribution of companies that got together to come up with a better Ethernet to address what RoCE v2 is not able to handle today. It's an open specification. The goal was to come up with APIs that will interface to existing AI applications or HPC applications. Optimal performance for both AI and HPC use cases, but rely upon the electrical and signaling characteristics of what IEEE 802.3 defines for Ethernet. So use the same signaling mechanism, use the same file layer, build on top to get a better performing transport layer and a better performing link layer. The congestion control, the way it is handled today with PFC, it was revamped completely now in the Ultra Ethernet, where you don't need to turn on. In fact, you have to turn off PFC for the Ultra Ethernet to work efficiently. The way the congestion is handled is now at the endpoints based on telemetry from the network and round-trip delay measurements. If the round-trip delay from an ideal network to a congested network is the delta, you try to avoid that path. We talked about scheduled Ethernet or enhanced Ethernet, where we can spray packets. Ultra Ethernet relies on spraying the packet across all possible paths in your network. And the path selection is done at the end host, where you, as a sender, decide which path the packet should take, and that is based on the congestion algorithms running on the host. So you are avoiding congestion by deciding not to take a specific path based on the telemetry that you received from your network and the congestion signaling that you received from the network to decide which path to take to the destination. And also, the other goal was to extend Ultra Ethernet to storage down the road, and that's something in the pipeline for UEC 2.0, but Ultra Ethernet Consortium specification for 1.0 is focused on the back-end network, which we talked about, which Scott talked about, the network that sits below the server, just used for AI inference and training applications. So that's the focus of Ultra Ethernet. So how did they go about doing it? So they came up with a new transport layer, not using TCP, not using UDP, not using InfiniBand protocol, but it's something completely revamped to use the Ethernet as a link layer. It's built on 3 independently large pillars. Security. So security is built into the transport protocol. Today, IPsec was added to the layer 3 protocol as to support security mechanisms. Here, the security is handled within the transport protocol, so it can work seamlessly across any kind of network you have. The second thing is the packet delivery sublayer, which handles reliability and congestion control or congestion management. And the third layer is the semantic layer, which basically interfaces to the software APIs and converts messages to packets that need to traverse the network. The API is defined in such a way that it maps to existing solutions that exist in the industry today. I will have us talk about that as to what the existing API interface looks like in the subsequent slide. But the goal here is any application running on AI fabrics today using NCCL, RCCL, whatever CCL library will interface seamlessly to the underlying hardware that exists that supports Ultra Ethernet. That's the goal. You replace the switching, you replace the NIC, the same application runs with a specific API sublayer modified to support the new hardware. So what are the key features and design goals when Ultra Ethernet started working to come up with a transport protocol? It should work in traditional DC deployments. That was one of the vision. Should be built-in security. And it should also work for AI/ML and HPC infrastructure so that you address all the supercomputing needs. The collective operation that we talked about, the all reduce, broadcast, they are designed very nicely to be handled by the network. All the GPUs send their data. What if the network did the in-network compute to reduce the data and then send the reduced data back to the GPUs? So the Ultra Ethernet Consortium is looking at how to improve the collective offloading to the network, and that's called in-network compute. It's going to be there in the standard products supporting in-network compute will be in the pipeline eventually to support any reduction or any broadcast today is handled for multicast and broadcast traffic. collective broadcast can easily be handled by the network. So that's the goal of in-network compute. So that said, the effort put together by the Ultra Ethernet Consortium is to make sure that the fabric works for best effort or lossy network or lossless network. There's no need for a lossless network like today Rocky V2 relies on the lossless network. That's why they enable PFC. Ultra Ethernet handles reliability in a different way that you don't need to have a lossless network. With the best effort network, you can still get the same performance that you need to get for AI training applications. Scalable, we are talking hundreds and thousands of GPUs interconnected using the Ultra Ethernet fabric. So that's the scale. We are looking at up to 100,000 GPUs to 256,000 GPUs. Flexible packet transport. So here you could do reliable ordered delivery of packets, reliable unordered delivery of packets, or unreliable unordered delivery of packets. You get to pick what kind of reliability you need on a per message basis that is the application is trying to send across the network. So that's the flexible packet transport. And the advanced congestion management totally relies upon round-trip measurements. So the packet is timestamped, it goes across the network, comes back with the timestamp of when the packet comes back, you have measured your round trip. You have an ideal round trip for any given path. The network topology could be whatever you want it to be. Every path has an ideal round-trip delay. If the round-trip delay is higher than the normal, and crosses a certain threshold, the end nodes decide not to use that path for spraying the packet for a period of time. And then the new round-trip time measurement happens in the background, and then so your adaptive packet spraying across the multiple paths that exist. So talk about the protocol itself, the software stack that exists today and how Ultra Ethernet coexists with existing. So you have the HPC applications, could be MPI, SHMEM, or any of the CCL. There's a libfabric API. Libfabric defines a communication API for all these high-performance parallel computing applications. It's an open source. Linux Foundation makes it open source for anybody to use. It is deployed in scale, and there is an ecosystem that exists to support any Ethernet NICs, any RDMA NICs, or in the future, any UEC accelerated NICs. And the abstraction layer provided by this API makes this application run on any of the hardware that you pick and choose. That's the goal. So the Ultra Ethernet providers will provide this mapping to map to the existing APIs and then deal with the hardware below it. And that's the goal of Ultra Ethernet, to make it seamlessly take an existing AI application or an HPC application and run on Ultra Ethernet hardware. So with that little bit of a brief introduction to Ultra Ethernet, let's revisit the AI infrastructure challenge. We saw that these three parameters that cause a big problem in the network, how do we address with Ultra Ethernet all three of these is the question. So improved load balancing and adaptive path selection is one way of avoiding congestion. Network influenced, so you have telemetry from the network, you are able to do the congestion management. So these three things basically introduces Ultra Ethernet as something between an enhanced Ethernet and a scheduled Ethernet. Load balancing is endpoint controlled with adaptive packet spraying. We talked about it. Based on the congestion in the network, the endpoints decide to avoid a specific path and use the other available paths for packet transfer. Fabric congestion management is network-influenced congestion management. And the link failure is built into the hardware, just like enhanced Ethernet or scheduled Ethernet. So from a job completion time, we think Ethernet is good, enhanced Ethernet is better, Ultra Ethernet is even better. Scheduled fabric still gives you the best possible bang for your buck to get the cross-functional utilization without having to change anything in the host stack. Ultra Ethernet requires a new hardware in the NIC, so it's tied to the, it's coupled to the NIC. Scheduled fabric does not. So you have to basically make a decision whether you prefer scheduled Ethernet or Ultra Ethernet. Ultra Ethernet is open standards. Scheduled Ethernet is, at this point, Cisco specific. And from a place in the network point of view, Ultra Ethernet is focused on back end. Down the road, a couple of years from now, they are going to see how to extend Ultra Ethernet to the front-end network as well. Any questions? So the transport layer is designed to work with IP as your layer 3. So you could be carrying an Ultra Ethernet transport payload using IP. The requirement from a network's point of view is you are carrying Ethernet packets with IP as your layer 3. Payload, most switches or most network devices don't look at the payload. So you could carry a transport, UEC transport payload with an IP header and a layer 2 header through any of the Ethernet switches today. The flexibility of what Ultra Ethernet brings to the table is endpoints are deciding which path to take. So you will disable packet spraying in your network and use the entropy in the packet to decide which path to take in the network. So all existing switches that we sell today supports Ultra Ethernet from that point of view. Make sense? I can't answer the question in a public forum, but let's talk offline.
They have their reasons.
Sorry?
They have their reasons.
NVIDIA is a well-known reason. The consortium is going after the, yeah. Okay. Any other questions on Ultra Ethernet? Okay. Give it back to Scott to wrap up.
Oh, I'm doing the wrap. We can both do it, right? Like,
okay.
Actually, go kind of like all these various things, various technologies you can use, right? They're open standards, right? Ethernet itself is an open standard. SONiC is an open standard. Ultra Ethernet is an open standard. libfabric, right? libfabric, I think, is going to be really powerful, and nobody's talking about it, but that makes it so that the closed standards of maybe the nickel, rickel, hickel all have an abstraction API that you can use to control, right? Because that's so important to how the jobs are scheduled and AI jobs, how the jobs are aware of the topology, and libfabric kind of looks to unite that. But our goal here is not to say, you know, we're gonna close everything off and be Cisco. The new Cisco is open, right? We just want you to consume Cisco technology, right? Whether that's our own software on somebody else's systems, our silicon in somebody else's systems. It's great if you want to buy both from us, but we've kind of realized in the data center that open standards are what take hold and are the best approach, right? Like a community involvement.
It's a question.
Go ahead. Kind of, but it's not, there's not a broad ecosystem of support.
IBTA might be, InfiniBand is open, but what you run on the stack, CUDA is not open. So the stack above the hardware is not open. The goal is, sorry? Transport is, yes, I agree.
True.
But the number of people making InfiniBand products versus the number of people making Ethernet products.
NVLink isn't. If you saw some of the articles on that came out last week on UA-Link, right? Again, it's that trend towards openness. All right, we have 80 plus developers working on Sonic right now. We're one of the largest contributors to the community. All right, this is not like kind of just something that we chose to kind of do. It's something that we're committing fully to do. Key takeaways. AI presents a new challenge to the way networks are built. Not all parts of AI need the same kind of network. Scaling up and scaling out with Ethernet gets the network out of the way. Choice of parallelism has a profound impact on cluster performance and our ability to reduce job completion time, scale out the number of endpoints, the number of GPUs. Cisco's Ethernet options are open, flexible, and ready for the AI challenge. One solution with Silicon One for any AI Ethernet fabric option. Thank you.